Hi everyone. In the last class, I had asked you to try and solve these two circuits. So in this class, we will actually go through a little bit of resistive circuits, and mainly we will solve equivalent resistance for some complex circuits and some interesting circuits which will find applications in analog circuits. Okay. So just to there is a small point before I delve into the circuits, the resistive circuits. I just want to mention a brief moment on the power and energy. So in the last class I said the energy is given by integral of power. It's actually the power here is the instantaneous power, okay, which is the product of voltage into current across any two terminal device. There is also something called average power, which we can define for periodic signals, which is the instantaneous power, the average of instantaneous power dissipated per cycle, okay, divided by the time period. So which is also defined as the average energy dissipated per cycle divided by the time period of the signal. So average power and instantaneous power are two different things. Okay, instantaneous power can be larger than the average power or smaller than, it's usually larger than the average power for a transient or AC circuit. And for usually we define average powers for periodic signals. For aperiodic signals we define only instantaneous power and energy. Okay. So let me go back to solving this problem. Okay. So in the previous lecture, I had just given you these problems to solve. I discussed this concept of using the symmetry to solve resistor circuits. So first, let me just redraw the circuit in a more well-known fashion. So I'll just straighten out these resistors, okay, these resistors as well, and then draw it in a more simpler form. So this circuit can be reduced to R. So can you see that these two resistors are in parallel? These two resistors are in parallel, and similarly these two resistors are in parallel. I'm not sure if the color is visible. Let me use. So the resistor here, the resistance here, and these two resistors are in parallel. So I can reduce them as R by 2 and R by 2, and this would be 2R. And similarly you would actually have 2R here, and this would come to R by 2 and R by 2. It's actually a pretty simple circuit, just drawn in a very fancy way. So it looks complicated, but it is not. So you're supposed to find the equivalent resistance between these two terminals. Okay, between these two terminals. Okay, so now you can draw the axis of symmetry around this line. So when you draw the symmetric point at this point, if you see the circuit is purely symmetric on either sides, okay, so from this arguments of symmetry we can argue that this point, the voltage at this point, the voltage at this point are same. So if I call this as V1 and V2, they are same, so I can simply short these 2 points. Similarly, the voltage at this point and the voltage at this point are same. Okay, so I'll use V3 for this. V3 and V3, they both are at same potential. Okay, so again I can short these 2 points. Let me just, these 2 points can be shorted. Okay, so this circuit actually let me just redraw the new circuit. Because these 2 points are shorted, these two resistors would come in parallel. So you would actually have R by 4. This resistance can be removed. The effect of the resistance does not matter. And you have R by 4, and the circuit further reduces to 2R, R, and R and R. So now the only problem with this circuit is that the additional resistor in this network, so wherein I need to know the current flowing through these two terminals. Okay, we know these two are at same potential, so obviously there cannot be any, since these two are same potential, you cannot have a direct current flowing from this end which goes into this. Okay, so using that itself we can say these two nodes are at same potential, so I can ignore. But there can be some special cases where that you cannot ignore the current through this, but so I'll just take a different approach to show that the current through this is 0. Okay, so how do we do that? We can go for Thevenin equivalent. So what I'll do is I'll first remove this resistance and try finding the open circuit voltage between these two node voltages. So let's assume we applied a test voltage Vx or Vt between these two terminals. So we know that this voltage is at Vt by 2. Now we have already analyzed a circuit like this. If the ratio of this resistance and this resistance is equal to the ratio of this and this, we said no current flows through this. Okay, so I might as well short this, and this voltage will simply be equal to Vt by 2. So therefore there is no current flowing through this as well. There is, in fact, since this ratio condition is met here, I can assume this can also be shorted. Okay, so since we are able to show the current flowing in this circuit here, I've just reduced this circuit here, what I showed it here, the current flow through this is 0, I can short this terminal as well. So the circuit can be further reduced okay, it can be further reduced by making okay, so this was R by 4, and we had a resistance of R here, I'm shorting it out, and we have a resistance of R, I'm shorting it out. Okay, so it's all shorted. Now the circuit reduces to a very simple form. This is just R. So the circuit is very simple to analyze now. You just have 3 resistors in parallel in the upper branch, which are again parallel in the lower branch, and these two are in series. So you can very easily show the upper branch resistance is R by 6, R by 4 in parallel with R and R is R by 2, which is in parallel with R by 4 will give you R by 6, and in the lower arm you get R by 6. The total equivalent resistance is R by 3. Okay, so that's how you solve this problem. In fact, you can just directly look at this circuit and then short. If you short these 3 terminals, you are done. You get your answer. Okay, now let's analyze this circuit. Let me just expand this a little bit. Okay, use a different color. So in this circuit, again I am going to draw an axis of symmetry around this point. So when I draw the axis of symmetry, the voltage at this point and this point will be same. So if this is V1, this is also V1. So similarly, this point and this point are also symmetric around the axis of symmetry, so this will be same, V2 and V2. So I can short this node voltage, I can short this node voltage. Okay, both these node voltages can be shorted. I can short this and this. So maybe I will use a different color. So I can short this and this. Okay, now since I've shorted this, my circuit analysis becomes extremely simple. So these two resistances will now be in parallel, so you will get a resistance of R by 2. I am at node V1 now. Okay, and from the node V1 you can actually see there are 4 resistors in parallel. So you have R, 2R, 2R and R, all are in parallel. Now this is at node V2, and then from V2 again you have a resistance of R by 2. Okay, so 2R and R parallel with R, 2R and R in parallel, you get R, and you have 3 R's in parallel, so you get R by 3. So the overall resistance of this circuit, let me use a different color here, it reduces to R by 2, R by 3 and R by 2. So the net resistance is 4R by 3. Again, we didn't use any KCLs and KVLs, we just used the arguments of symmetry to solve this problem. Okay. So now I'll go to another very important circuit which is called as the R to R ladder. So first let's assume you have a circuit like this, R and 2R, R and 2R. and the final resistance, only in the final arm I am going to connect a resistance of R and R. Now you apply a voltage Vref to this. I want you to find the node voltages V1, V2 and V3. At these 3 points you need to find the voltages. Okay. So how do we go about this circuit is we start from the end. These are all grounds. These are all ground points. We start from the end. The resistance seen here is 2R. R and R in series, you get 2R. Now the resistance seen at this point at node V2, so we can actually write some simple relations. If you see node V3 here, V3 can be written as V2 by 2, right? It's a simple potential division. Both Rs are in series, you get this. Now to find V2, okay, I'll see at V2 the resistance seen here is 2R in parallel with 2R, because the resistance seen here is 2R. So that would reduce to, I'll just draw this part of the circuit. So this is V1, this is R, and that reduces to 2R in parallel with 2R, that is R. So again you can write V2 is V1 by 2. Okay. So we have seen the resistance seen here is R, the resistance seen here is 2R. Now if this resistance is R, what is the resistance seen here? It will be R plus the equivalent resistance at this point, which is 2R. Now that would come in parallel with 2R. So the resistance seen at this point after 2R would be R itself. 2R in parallel with R will be R. So now I'll draw the point where we start at Vref, and this is R. So the equivalent resistance at this point is R, because you had a 2R at this point and there is a resistance of 2R at this point. So the parallel equivalent of that is R. So the voltage V1 is simply Vref by 2. Okay. So the equivalent resistance, okay, if you want to find the total equivalent resistance at this point, so let me just draw the resistances alone. This is R, 2R, R, R and R. So the equivalent resistance of this part is 2R. That comes in parallel with 2R and you generate R. So the circuit reduces to R and R. Again R and 2R here. So again the equivalent resistance at this point would be 2R. So the circuit further reduces to R, 2R in parallel with 2R, which would be R. Again the resistance seen at this point is 2R. So if you see in this network, the equivalent resistance seen at this point is 2R. Okay. The interesting observation that you need to make here is when you look at it from the resistor R, the parallel branch, the branch resistor at this point, the resistance is 2R here, the resistance was 2R here, and the resistance was 2R here. It was always the same. When you look into the node, however, when you look into a node at this point, just after the resistance 2R, it was R. It was 2R in parallel with 2R, so you are getting R at this point. Okay. This network is called as an R2R ladder. It's extensively used in data converters. I mean, when you're converting digital signals to its equivalent decimal values. Okay. And also it has a very interesting property. As you progress, every node voltage will be half of the previous node voltage. Okay. Every node voltage will be half of the previous node voltages. And so let me extend this concept. Since the resistance remained constant, I now add infinite such R2R branches. Okay. And the final branch I am going to make it as R and R. Okay. So when you do such a connection, when you make such a connection, at every node you are going to see 2R. I mean, no matter how many branches you have. Okay. At every node, I mean, when you are looking into the resistor, you see 2R. When you look at it after the resistance, the parallel resistance 2R, you will see a resistance of R. Okay. And the equivalent resistance at this point is going to be just 2R. No matter how many networks you connect, how many such R2R networks you connect, if you terminate the final point by resistance of R and R, you are going to get you are actually going to get a equivalent resistance of 2R at the input. Okay. So this is a very interesting circuit called as an R2R circuit. Each node voltage will actually reduce geometrically by a factor 2. Okay. That's it. So this is all about art resistor circuits. And if let me just give you some small circuits to test your understanding of basics of resistors so far whatever we have discussed. So if I have a resistor and a voltage or DC voltage source, say of value 1 volt, and I have a resistance of value R, what is the equivalent resistance at this point? And I have a resistance and I have connected a current of 1 ampere. Now I'm asking you to find what is the equivalent resistance for this circuit looking at this point. Let me give you a few more circuits. So I have a resistance network like this, and I have a independent voltage source connected of value 1 volt across this network. So you're supposed to find what is the equivalent resistance. Okay, all the values of R. Okay, in terms of R and 1 volt, only the parameter that is just shown in this figure. And this is 1 ampere, this is 1 volt, this is R and R. Now you are supposed to find the equivalent resistance seen at this node. Okay, so here when I ask you to find the equivalent resistance, if you apply, when I say equivalent resistance between these 2 points, so if I apply an incremental voltage delta V, you are supposed to find the incremental current delta I flowing through this network. Okay, and so try finding the value of equivalent resistance for the circuits I have shown here. Okay, this is just to strengthen your understanding of resistors and independent voltage sources. Okay, thank you. I'll stop here.